Welcome back to part 2 of 3 of reliability models. In this part 2, we're going to talk about the Weibull and the Poisson distributions. We'll start with reviewing the model with the existing distributions, which were the triangular and the exponential. We're going to understand the differences in the Weibull and the Poisson. And then in part 3, we'll incorporate those distributions in the model and propose a budget solution. Here's our Excel model. We'll define the inputs up here as a discount rate of 8%. We've got a mean time between failure of 250. Time to repair is 7, 14, and 40 we talked about. And the cost to repair is 1,000, 1,500, and 3,000. What I've done to make this more like a simulation over time is to replicate the failure, repair 7 times, and to use these distributions, resampling it each time. So I have here, I have my exponential distribution, exponential, and then I have the triangulars coming down here. Coming down a little bit further, we can see the cost to repair as a triangular distribution. We can get the total cost to repair. We can calculate the NPV because we have the time for each one of the repairs, a date, and we can calculate the NPV based on those dates. Down here, I have calculated the probabilistic results for various metrics. Here are the graphs we showed here for failure time per cycle and the repair time per cycle. As we come down further, we can say the failures and repair schedule that I showed in one of the slides. With SIPmath, we can look at a number of different trials. So over here, I went to the SIPmath tools, get trials, and then we can just scroll through 1,000 of these if we so choose, and you can see they're moving up, they're changing over time. And we, as we come down further here, we can see the NPV for the 7 cycles has a cost of $10,000 with this kind of a distribution, 7,000 to 14,000. And finally, down here, this is showing the repair cost uncertainty by year. This is the expected. And this represents the P10 outcome. So there's a 10% chance that we won't have any costs in any year or in any given year. And there's a 10% chance that it could be as high as, like $5,000 drifting down here to 4,000. This red line represents the current simulation. So once again, if I come over here to trial information, as I flip through these trials, you can see what happens here. In this particular case, I actually spent nearly 7,000, even though I said the P90 was only 4,000. Remember, there's a 10% chance of being above this line. I can't be actually below 0. Okay, so now let's talk about the Weibull distribution. And we wanted to compare that to the exponential. So here is the exponential distribution with my 250 days. And it's shown here as the blue line. The Weibull distribution, shown here, is the red line. And as you can see, here at 121 days, it's a 31% chance that I'll be less than 121 days with the Weibull. But if I go up a bit, we see that there's like a 40% chance with the exponential. So I'm going to have longer run times initially with the Weibull, but then I'm going to have shorter run times later on because of the aging of the equipment. So let me just demonstrate something. let me redo this distribution for you. You can see this is a long equation here, but we don't actually program that. SIPmath is going to do that for us. Let me just get rid of that, and you can see the distribution went to 0 because it's being recalculated over time. I'll just come back in here and generate an input, generate the Weibull, and it's going to ask me for the lambda, which is really the mean here in this case, tab, k, tab, tab, and this is the seed. Okay? We'll talk a little bit more about the seed in a minute. And I'm back to where I was. This is the exact same distribution with the exact same outcomes that I had before. So you can see how easy it is to generate these distributions. Okay, on the Poisson, we have the time to repair currently characterized as a triangular distribution with 7, 14, and 40, and that is shown as the blue line. And we want to consider a Poisson distribution here. Similarly, I'm not sure why it's such a small font. Oh, there we go. This looks like a complicated equation, but once again, SIPmath will program that for us. And we have a lambda. So the lambda, we need to adjust. If we wanted to have the Poisson to have the same expected values as triangular, if that was the objective, then we would need to be up here at around 22. I can put in a 21, see if that's a little bit closer. That's a little bit closer. I can put in a 21. And now that's similar, have an expected value. But the Poisson, what happens is, this is the days to time to repair. It's going to be a little bit longer early on, but then I don't have the downside long repair times. If I made this a 1, it identically equals the exponential distribution. If I make it a 2, or a 3, or a 7, you can see what happens to that distribution. I just feel like 1.5 feels right. If you had some data, you could fit that. Remember, having a subject matter expert assessment, no matter how bad it is better than any deterministic result. Please join me for part 3, when we will look at incorporating these distributions in the model and propose a budget solution for the reliability of our machine.